Okay, you had a bunch of pages like this. I think they were pre-lecture notes number 7. Most of that's just for your own reading. Again, we kind of summarized many things for you. But I'm going to go over some of the parts that are relevant for the homework and then move on. FTTX, X can stand for anything. H, that it's fiber to the home. P is premises. C is curb, would be kind of to your neighborhood. Fiber to the node. You know how to read. So let me just point out a couple things about some of these pictures. There are different architectures, different ways of doing it. From the central office, right? If you have one fiber going to every single house, you can look up what that stands for. Optical network terminator. Can't have enough acronyms in telecom without making up some more. This is where it goes from optical over to electrical so that you can see it. Because your computer is electronic and not optical computer yet. But that's a lot of fiber, isn't it? You got fiber going to every single house from the central office. It's more expensive because you've got a lot more fiber than these other architectures. And wink, wink, nod, nod. Here's another one called active star, where everything O here is optical, so that's fiber. And then there's fiber going to each home here, but only coming from this point. Right, so there's less fiber being used here, as opposed to having fiber going to every single house from the central office. So it goes to some active node. The word active here, as opposed to passive. Active means I plug it in, and I'm having to plug it in means there's electrical power. All right, so what's this O/E/O thing? That's a regenerator. So we don't have an all optical pulse regenerator. I'm working on it. Other people are working on it. We don't have them in the industry yet. But that would be nice, because then you wouldn't have to plug this thing in, right? Then it could all be a passive optical network, all optical. Nice and cheap. But here you take your optical signal, very high data rate, and you split it out into many of these lower data rate electrical signals, and then in each one of these you regenerate the signal. You set a threshold, and so this is optical, then oops, this one's electrical. So we electrically regenerate everything. So this needs some electrical power. Makes it expensive. So I have these crudded up pulses. They're all noisy and cruddy. And then I regenerate them in nice clean pulses. And then I bring it all back up to optical. And then go back out the door. Okay, but that means somewhere I've got to have a building, because I have to run electrical power to this node. Okay, this is a regenerator. I think we'll say more about that in class live. It'll be more fun. But this is going to require electrical power. What's another way of doing it? Passive optical network. Pawns. No electronics. Nice. I don't have to power anything, right? But if I'm going to have a splitter, it's got to be optical splitters without requiring any electronic switching or anything. Couldn't be part of a passive optical network. And here, an example would be have a passive optical network all the way up here. And then you go down to one of these ONUs, ONT, you can look up what that stands for right here on that page. But the point is, this goes out to a certain location where this is all passive optical network out here. And then you've got cable, copper, DSL, etc., coax going to the home from there. So this is like fiber to the curb would be like roughly, fiber to the curb here would be roughly, it's fiber, it's passive optical network, it's fiber all the way out to some box that sits in your neighborhood, maybe a block, right? So that's fiber to the curb. And then the rest of it's copper that you already have in your house, right? AT&T was wise enough to put more bandwidth in the copper cabling than everyone needed because they figured, you know, someday people might have computers in homes. So they built that extra bandwidth right in from the start. Okay, let's shift gears a little bit and talk about noise and photodetectors. I shine some light on a photodetector. It's basically a diode, but the optical signal comes in and it turns into an electrical signal. So on the electrical side of my photodetector here is a current, and it's proportional to the optical power that came in. Or the proportionality constant here is called the responsivity. A certain number of electrical amps out per optical watt coming in. For silicon, the responsivity is roughly non-zero from 400 nanometers out to 1125 nanometers. Right? It would work for 1550 nanometers, which is out here. Right? So we use different materials. But I'm mentioning silicon because it's all over the place. Silicon has its peak near 850 nanometers. So back in first generation, that would have been the photodetector to use. But these are good for solar still. That's why your solar cells are typically made out of silicon, because it's got good responsivity where the sun is nice and bright. Anyway, no matter what it's made of, every photodetector has its own noise. So the signal, the current, the electrical current coming out of it, is that which we said, which was some number times the optical power that came in. That's my signal, that's good stuff, but then, yes, plus some noise, right? So we call it shot noise. Shot noise has a Poisson probability distribution function. PDF stands for probability, you can write it, distribution function. See why we just call them PDFs. It's the probability, right? So I shine light on a photodetector, and then I hook the photodetector up to a speaker. So every time a so-called photon comes in, I hear a click. What's really going on is the energy is being extracted from the quantum electromagnetic field, and it's kicking electrons up into the conduction band to where they can move, and then the discreteness of the electrons is what's causing the click. I don't need to think of light as a particle. I don't. I have a PhD in quantum optics. So in here is really, just think of it as the number of clicks within some t-second observation window. So I've got some, I observe for whatever t is, maybe it's a millisecond, make it whatever you want. I listen for a certain amount of time. I hear one click, and then I hear, next time I interval, I hear click, 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 and then I hear click, and then I hear click, click, and then maybe the next time I don't hear any clicks, right? So here's the number of clicks. The probability of hearing one click or two clicks or 0 clicks, right? 0 clicks can happen. It has a non-zero probability. I never hear a negative click. But this thing goes on in principle out forever. Maybe I hear 1,000 clicks. mathematically, that distribution looks like this. It's not so bad. You all, you're not gonna have to use this part, so I'm labeling this as an aside. But just to get you some further experience with probability distribution functions, this is one, you're already friends with these formulas. Take some number, I'm calling it mu, call it A for anything, raise it to the n. You know what that means. A times A times A, n times. That's exponential growth. You know all about that. In factorial, well, if you haven't seen it before, it's not that bad. In factorial, so that could be 7 factorial, then it would be 7 times 6 times 1 minus that would be 5 times 4 times 3 times 2. That's what in factorial means. And to make that work, you also have to add in, what do you mean by 0 factorial? Making that 1 makes it work. Probabilities have to all add up to 1. That's called a normalization constant that makes that work. If you want the fine print on that, it's that. And this number mu here turns out to be the average value of n. Okay, so side, end of the side. Now, back to stuff that's not in the side. So the Poisson distribution has this interesting property that the average value of the number of clicks, rather than calling that mu, let's call it capital N. It's the average value of n. That's proportional to the power, right? The number of photons, if you want to call it that. And the variance turned out to be the same number. Doesn't always happen. I can't think of any other place than Poisson that has this property. Okay, so what's this variance thing? Probably heard the words. Square root of the variance is called root mean RMS, or root mean square. Well, I can take this as the definition of it. The pointy brackets mean average. Okay. So n is a random variable. Pointy brackets around it means average value of that random variable. That's where, you know, if I made this out of wood, if I had these little tinker toys and each one was that high, so that each one weighed that much, I put it on a stick, I try to balance the stick on, it would balance at its average. That's geometrically what average means. You know what average means. Right? So if I take the random variable, subtract its average, and then I square it to make it more like a power or something, and then I take the average of that, that is what we mean by variance. It's a measure of how much it moves around outside of its average value, how much spread is there in that. Now I'm going to go ahead and focus on this one because it might help you on the homework, right? Let me write this out. This is the definition of the variance of the n. Okay, just write it out. Then it's the average of, all I did was I squared that. I got a plus b squared. So I get a squared plus b squared plus the cross term, 2 times a times b. That's all I did there. You don't have to do this part yourself, but you might want to use the result I came up with. And it's linear, so I can just take it term by term. What's the average of n squared? Well, it's the average of n squared. Right? What's the average of 2 times x, where x is a random variable? The average value of 2 times x would be 2 times the average value of x. Right? So this is a number 2, it factors out. In, some people put a bar over it, in bar, but the average value of n is a number, so that factors out. Then what am I left with in the second term? N. average value of n, write it this way. So there's a second term. The third, last term. What's the average value of 17? Well, 17. So average value of the number is just the number, right? So that pops out. Then I notice, oh, hey, wait, this is average value of n times average value of n. So minus 2 and a plus 1 gives me a minus 1. And so the variance, even though we defined it to be this, oftentimes you calculate it this way. So notice in a Poisson, I know that the average or the mean average value of n and the variance are the same number. And so if I want to solve for this, which is called the second moment, I've got it right there. Okay. That's true for any random variable, whether they call it n or x or I. Okay. This shot noise stuff has a spectrum, has different frequencies in it. Right? So here I'm going to take some light, and if I shine it on a photodetector, I can plug that current into a spectrum analyzer. Instead of hooking it up to my speaker, I can hook it up to an electrical spectrum analyzer, and that signal I'll see its spectrum. If it's maybe typically 10 gigabit per second. If it's binary AM, then that's going to be around 10 gigahertz. Right? But here's my frequency bandwidth, centered at whatever carrier frequency I'm at. I could, rather than using an electrical spectrum analyzer, I could split off some of that light. This is a beam splitter, which is just a piece of glass, usually just drawn with one line like that. Some of the light goes through, some of it reflects off. So I can tap off some of that signal and send it into an optical spectrum analyzer. These are a lot more expensive than those are, right? And because it's basically got a prism in it, and it splits the light into all the different colors, and then I have a photodetector for every different color. Yeah, so very, very expensive. And then this would show me the spectrum, the optical spectrum, which is going to be around 1550 nanometers for a typical system. So a spectrum analyzer shows me the distribution of all the, how much power there is at all the different frequencies. Here's an example of some spectrum. Amount of power is a function of frequency. This shot noise just keeps going up and up and up. It's linear with frequency. Right? So at low frequencies, there's not much shot noise at all. At higher and higher frequencies, shot noise just keeps getting stronger and stronger. Contrast. Let's contrast that with thermal noise, which is like, rub your hands together. That's temperature, right? What you're feeling is the electrons are moving back and forth, and the hotter they are, the more they jiggle back and forth, right? So moving electrons looks like a current, but these are moving randomly, so it's just noise. So thermal noise has a spectrum that goes like this. It's flat over the bandwidth of most electronic devices, and then it drops off. And the break point at which it kind of drops off here is maybe around microwave frequencies. So when you get out to the frequency corresponding to optical telecommunications, shot noise is huge compared to the thermal noise. That's the noise that's in the field itself on the optical side. Right? So if someone says at optical frequencies, they're talking over here. Right? They're talking, well, here. Right? At optical frequencies, which one of those is bigger is pretty clear. Right? But that doesn't mean that when you're over here, after the photodetector, if you've got a lot of thermal noise, the thermal noise could actually dominate if you're on the electrical side. Now, although shot noise, I said it climbs like that, and it does, but if you're in what optical people would call a small electrical kind of bandwidth, like 10 gigahertz or something, that looks roughly constant. It's roughly flat. And so in books like Agarwal's, it'll say, well, shot noise is going to be like this. It's roughly constant. You have a certain band of frequencies that's going to scoop up this much of it. The height here is 2 times the charge of the electron times our old friend, which was the current signal was the responsivity times the optical power coming in. So as I increase the light shining on the photodetector, the amount of shot noise will go up. Now, we said that the shot noise is Poisson distribution, but here's its average value, capital N, and when that gets really big, this Poisson shape starts to look kind of like a Gaussian. It's like almost everything turns into a Gaussian if there are enough random variables that are being added up. Something called the central limit theorem that proves that it doesn't matter what they started out as. If you've got a lot of them, they're going to tend towards a Gaussian. So here's a better drawing of what a Gaussian looks like. And it has a certain spread to it that's reflected by its variance. I'll come back to this Gaussian shape in a minute. So even though shot noise is Poisson, you could approximate it with a Gaussian, and then you could figure out its variance, the kind of the noise power here, if you want to compare it to thermal noise, would be the height of that spectrum times the frequency bandwidth that you're in. I'll leave it for you to sort out what do you need for the homework and what is just furthering your education. Let's take a look at the thermal noise. We said it had a Gauss, well, no, we didn't say anything yet. We said this part. We said spectrum looks like this, that it's flat out to where I get up to infrared frequencies. So over the bandwidth of electronics, you can approximate it as flat. That's sometimes called white noise because white is really all colors in equal amounts. And then when it starts to get some shape to it, then it's called pink noise. It's got a little coloration to it. Probably would just be white. So you've probably heard of white noise. This is additive white Gaussian noise. This is the big bugaboo in electronics. And the height here is given by 1/2 kT. K is Boltzmann's constant. T is the temperature. The hotter things are, the more thermal noise I have. So I can get rid of thermal noise if I cool everything, but liquid nitrogen doesn't come cheap, right? So that's expensive to try to cool all your electronics down to where the thermal noise gets smaller. The other thing about thermal noise is it has its own little PDF. Instead of a Poisson, it is exactly a Gaussian. Right? And the shape of this double-shaped curve, if you want the fine print, goes like e to the minus v squared, where v is the voltage, right? And divided by the variance with an unfortunate factor of 2 that shows up there too. The number that goes out in front is just whatever you need to make it normalize. In other words, it all has to add up to 1. Something has to happen. So the normalization constant turns out to be that. But the variance here tells you how wide this thing is going to be, right? What's the average value for the thermal noise? It's 0. There's no reason for any bias to it. There's no reason for, it's just randomly jittering electrons. There's no reason for them to drift more to the left or more to the right. So the average value here is 0 for the thermal noise. Well, that's more than you need for the homework, so have fun with it, and we'll see you next time.